So example 6.1.1. So finding probabilities in a uniform distribution. So again, we're going to come back to this example where the commuter trains on the blue and green lines for the Regional Transit Authority in Cleveland, Ohio have a waiting time during peak rush hour periods of 10 minutes. And again, we're going to assume that that has a uniform distribution. So part A says to state the random variable and draw a picture of its distribution. So our random variable here is the waiting time during peak hours for a randomly selected commuter. Now we could also be more specific there and put on a blue and green line in Cleveland, Ohio. Okay, but again, this is good enough. And then it asks us to draw a picture of its probability distribution. Okay, so for this one, we had a picture earlier. Okay, so from 0 to 10, and it's uniform over that interval. And this total area here, we're looking at probability, needs to be 1. So if the whole base here is 10, that means the height has to be 1 over 10, so that when we multiply those together, we get an area of 1. So the height of this curve here is 0.1. And again, this is our random variable x. All right, so now for part B, it says to find the probability that, okay, so probability that, those two words tell us we have a p parentheses. Okay, so find the probability that you have to wait between 4 and 6 minutes for a train. Okay, so waiting time is x, and we want that to be between 4 and 6. And it didn't say between inclusive, so there's no equal sign, but again, we know from up above this will be the exact same probability as if those endpoints were included, because we have a continuous random variable. All right, so in our picture here, this probability that we're after corresponds to this red shaded area. Okay, so this equals the red shaded area. Well, on your printed page it's not going to be red, but so the shaded area. Okay. So to get the shaded area, it is a rectangle, so we're going to take its base. So to get its base, we would take 6 minus 4. And then we need to multiply by its height, which the height everywhere here is 0.1. So we would multiply that by 0.1. And so that gives us 0.2. So the area of this shaded region here is 0.2, which means in the context of the problem, and again, relating this back to the idea of probabilities, that means that there is a 20% chance that a randomly selected commuter will wait between 4 and 6 minutes. And again, we could add in here, so I'm going to say that one of these, just so we know we're looking at peak hours in Ohio on this particular line, that they're going to wait between 4 and 6 minutes. Okay, so there's one way to do that interpretation for an individual. Okay, the second way that we learned how to interpret probabilities at the beginning of this unit back in Chapter 4 was that percentage of all of the objects. So we can also say that 20% of all commuters will wait between 4 and 6 minutes. And again, by all, we mean all of these commuters for this particular line in Ohio during peak hours, if we were to add all of those details in there. So again, two interpretations for probabilities, for an individual or the percentage of all. All right, so for part C, it says to find the probability that you have to wait between 3 and 7 minutes for a train. So again, our wait time for an individual is the random variable x. Between, we've got our two inequalities at both point left, and we have 3, 7. Okay. So we want the probability that 3 is less than x is less than 7. And so again, our shaded region here, so here this starts at 3 and ends at 7. So to get the area of that shaded region, we need the base of that rectangle, so 7 minus 3. And then again, the height everywhere for this rectangle is 0.1. So again, if we make this computation, we get 0.4. So with respect to the picture, the area of the shaded region here is 0.4. But that represents, for continuous random variables, the area under the curve represents the probability. So when we go to interpret this, again, we can interpret this two ways. So we can either say that there is a 40% chance that a randomly selected commuter will wait between 3 and 7 minutes, or we could say that 40% of all commuters wait between 3 and 7 minutes. So we'll find out later when we start dealing with inferential statistics that sometimes we are interested in what will happen to an individual. So in this case, a 40% chance that a randomly selected commuter is going to have to wait this long. But sometimes we're interested in the percentage of all of the population that falls in some particular category. And so in this case, the second interpretation is what we would be looking at. So in these initial chapters, we're going to keep interpreting things both ways, just so that we are comfortable with seeing that, again, it can be either used for the individual or the percentage of all in the population. All right, so for part D, we want to find the probability that you have to wait between 0 and 10 minutes for the train. And so in here we have the entire distribution shaded, so it should make sense that this should be 100% or 1 from our probability rules from before. But again, if we take our base of our rectangle here, we have 10 minus 0, and then our height was 0.1, so we do get 1, or 100%. Okay, so there is 100% chance that a randomly selected commuter waits between 0 and 10 minutes. So from an earlier chapter, we would call this event in here a certain event. All right, now part E, we want to find the probability that you have to wait exactly 5 minutes. Okay? So back in chapter 5, when we were dealing with the binomial distribution, when we wanted x to be exactly a number, we used binom PDF because we had a discrete distribution. X only took on whole numbers, and each of those whole numbers had attached to it a certain probability. Okay, but now we're dealing with a continuous random variable. So we want the probability that x equals 5. But this is now a continuous random variable. So this means if we were looking at on our distribution here from 0 to 10, we would be looking at an interval that starts at 5 and ends at 5. Okay? So the base of our rectangle would be 0 times the height of 0.1, so there is no area under a curve at a single point. So there is no area under a curve at a single point. which is why earlier we had said it doesn't matter on the ones involving intervals whether the endpoints are included or not, because if they're included, we just get, solid lines on the side of the rectangle versus dashed, but those little line segments don't actually add any area. So notice that in example 6.1.1.d, the probability is equal to 1. Okay, this is because the probability that was computed is the area under the entire curve. Okay, and for probability distributions, that has to always be 1. So just like in discrete probability distributions where the total probability was 1, the total area under the curve, entire curve, is 1 for continuous distributions. Okay, so this... For continuous random variables, we are going to be looking at probabilities as corresponding to areas under the curve. Okay, so this is the reason that the height of this curve above had to be 0.1. So we said the base was 10. Okay, so we needed the height to be 1/10 because 10 times 1/10 is 1, so that the total area of that rectangle was 1. Now we're not going to need this formula, but in general, if we were given a uniform distribution that ranges from A to B, so let's say that it was like from 2 to 8, okay, so from 2 to 8, okay, that means the base of that rectangle would be 6, so then that means the height would have to be 1 over that difference, or the height of that rectangle would be 1/6. Okay, so again, this is just a way of mathematically putting in with variables how you would compute that. But again, it's just whatever the base of that rectangle is, it's just 1 over that base, so that when we take this times the base, we get a total area of 1. All right, so the important concept to get in this very first section is that for continuous random variables, probabilities will correspond to area under a distribution curve. And in this first section, we're starting with uniform distributions because their areas are, we're finding areas of rectangles, which we already, from previous math, we know how to compute those areas.